morning. Everybody hear me out there? Sound check, very good. So, Wally, when you look out at the industry, we're looking at a lot of very fundamental changes that are going on right now. We're seeing this slowdown. Some people are in denial of this, but we are certainly seeing some sort of difficulty in getting to the next advanced nodes. We've seen consolidation. We've seen new materials coming in, new challenges in terms of lithography at the advanced nodes, new packaging approaches. What's happening, and what's the big shift that you see, and what are the problems that we're starting to encounter in the industry that will change what we're doing now for probably years to come?
Well, I'd say it's a more disruptive period than we normally have because there are more things changing. The good thing about all this disruption is that's the only way we grow our business. Although we don't like to advertise this, established design tools have fairly flat markets. Simulation, place and route, PCB. These markets don't grow particularly. What grows are new capabilities. So while the PCB design market hasn't grown, all of the signal integrity products that go with PCB have grown. And while the simulation market hasn't grown, the things you add on to simulation to handle new problems have, and emulation has grown as well significantly. And so with every generation, there's something new. And so every node, 10 nanometer, 7 nanometer, 5, there'll be new tools because there'll be new problems. So that's all good.
But we're seeing at the, when you look at whether you define it as 10 or 7, depending upon whether the back end of line is the delineator or it's the line width itself, or it's some other device, whether it's the FinFET or horizontal nanowire. There's more things that have to be considered at each new node as we move forward than there were at the past, right? So I've never seen you had to do all the worry about dynamic power, as well as static leakage, as well as other physical effects, narrow wires, RC delay in the wires, how you're going to print something on a mask, how many different layers of printing you need. So that's all brand new at once. It's been one at a time in the past.
Yeah, a lot of challenges, but every node has its challenges. And the great part is, if there are new problems, then you need new tools, or you need enhancements to existing tools, and that's what keeps the industry going. But I agree, 100 layers for a design at 7 nanometers, or somewhere in that lifetime generation, this is getting to be pretty complex, and so the problems that go with it are complex, but each generation introduces something new, and they can be small, like ESD protection. No one worried too much, but the foundries worried because you would blame them if the yield was low because you mishandled the wafers, and so the foundries eventually said, hey, we want to put our own standard verification in for your ESD structures. And it created a whole new business for us. The electrical rule checking, programmable electrical rule checking PERC was something that you never had to do before. And now, not only are they doing ESD protection verification before you get your design into the foundry, but now they're doing electromigration checks, and they're doing all sorts of physical layout checks, and actually it's almost like iPhone apps. It's every time I go to a company, I find they've done something new in programmable electrical rule checking that allows them to check for something they didn't have to check for a generation ago.
One of the big problems that we keep hearing about is functional verification, how you get full coverage of a very complex chip. How do we solve that problem?
Well, you'll never get full coverage, so, for starters, but we do have, with remarkably efficient analysis, we end up with a surprising number of chips actually being production worthy on a first pass or first pass plus a cleanup pass. If you looked at the state space of the average integrated circuit, you'd say, yeah, that's really surprising you can do that because you're checking so little of the state space. I think the thing that has changed is that even if you put pre-verified blocks together, the amount of verification still grows as the square of the number of gates or thereabouts. And so the problem just gets bigger. And one way to handle it is to do it faster. And so emulation, which was a pretty sleepy business for about 10 or 15 years, about 4 years ago, just all of a sudden doubled as new businesses fell off the cliff. Networking in particular needed to bang hundreds of millions of packets against ports to look for drop packets and things like that. And it was just impossible. Simulation just couldn't do it. And so everybody got an emulator. And that's happening industry by industry as the problem gets more complex, but they are getting the coverage, they're getting the designs to work. And then the other way from just do more cycles of verification is do smarter cycles. And so lots of progress on the formal side and on other approaches that allow you to do verification in a more efficient manner.
One of the big changes that we're seeing in the market, though, is that you're not just dealing with a 2-year cycle on a smartphone. Now you're dealing with potentially designing for an SoC inside a self-driving car, which is going to have to last 10 or 15 years. So the verification problem is completely different for something like that, isn't it?
Well, the problem of automotive electronics and the fact that you don't buy a new car every year or two has been around for a while, as so many of you know from having bought cars that had built-in cell phones and things like that didn't last very long. That one will come from upgradeability. I think there's a fundamental dynamic going on in the automotive industry to solve several problems. One, of course, is the proliferation of electronics and software, hundreds of electronic control units spread through the car, 100 million or more lines of software code, and then the security issues, infotainment, driver assist, and then driver assist morphs into self-driving. This one's a lot of change at once, but one of the things that becomes obvious to all the car manufacturers is for security reasons, they have to isolate safety subsystems effectively. Some would say you can't even allow electrical connections. I think we heard in the keynote yesterday that they think you can allow electrical connections if you make them very secure, but that changes the architecture of the car. The embedded software is, no matter how good you are at embedded software, you are not going to write 100 million lines of code without bugs and doors for hackers and other things. So the answer is you have to be able to update quickly and easily. And I think Tesla has set a model for the industry for being able to do that. 24 hours and update the whole fleet. I think it's going to be a long time before legacy gets it, but that's going to be another necessary requirement.
But as you well know from having updated your computer, over a period of years it starts running slower and slower and slower. So we've never gotten to that point in the car industry where we've had years of updates and incompatibilities and things that we've never pondered before.
Well, I think they would be delighted if you were forced to buy a new car every 3 years because the electronics had become unwieldy. I think that people are probably not going to do that, so there will be ways to retrofit. But it's going to be a little different world. Just in the connectivity of a car, for example, we deal with one in the maintenance side, unrelated to our embedded software that goes in the car, is the wire harness. And today, anyway, something like 1 in 3, 1 in 5 cars has a custom wire harness. So if you don't take the little wipers on the headlights, they don't run a wire there because wire is expensive and connections are expensive. And if you don't take a GPS, they don't run wires for the GPS either. And so it ends up, your wire harness is different from every other car because it's unique. So when you pull it in to get it repaired, all of a sudden they have the problem of, gee, is the yellow wire connected to the orange wire, and where's that go, and so on. And so you have to be able to enter a vehicle identification number by car and download the wiring diagram for that particular car so that you can work on it and find the problem. And that's something that has to be supported through the whole infrastructure, and is now, but is still a long way from being fanned out to all the companies and all the service locations and things like that.
But the goal is that these things don't break down as fast, right? I mean, that's been the model behind this whole idea, and we as chip makers are now suddenly in the liability loop for if something goes wrong in a self-driving car. Chip makers get dragged into this now.
Yeah, this is a testy area. So most of our industry, EDA, and most of the semiconductor industry is very reluctant to accept liability for recalls, accidents, other things for the small price of what they sell into a vehicle. And the new entrants into the automotive space understand that. Some of the long-term automotive suppliers still believe they rule the world and can force that liability down. And so I think there'll be evolution over time, but I expect that if you're going to have innovation in the automotive industry, you're going to have to protect your supply chain at some level and limit that liability going forward, and especially self-driving cars where even the car manufacturers are sort of testing the water. Tesla has well, you touched the turn signal, so it was you who caused it to change lanes, not the car, and that kind of thing, and that's sort of being tested now.
You've been dealing with the automotive industry for quite a while. As a matter of fact, I think everybody was rather surprised when you jumped into the wiring harness business when nobody else in this field even thought about it. How have the relationships and the demands of the tier ones and the automakers changed on EDA and also chip makers versus what they used to be?
Yeah, so a big change. We actually introduced our first wire harness product in 1992. And I just have to say, if you're impatient, this is not an industry to work in because adoption takes a lot of time, and especially for an enterprise product that has to be supported by all parts of manufacturing, design, and so on, it's very laborious. I doubt that we would do it again if we hadn't spent the last 25 years building the relationships. But the thing that's changing is the hierarchy of the automotive OEM tier one semiconductor supplier. And the automotive OEMs are very sensitive to the fact that their supply chain, their ability to react and move quickly is limited by the embedded software that's wrapped around chips in ECUs that are supplied by their tier ones or semiconductor companies that are wrapping more embedded software around their chips. And they would like to be, well, I can't say free of that, but they would like to minimize that impact. So one of the first things that happened was about 12, 14 years ago. AUTOSAR as a standard started really taking hold, and so that was something we got into very early. And AUTOSAR is a way for them to have standard interfaces and move execution from processor to processor. Another thing that happened was OEMs started driving the system architecture through the embedded software for systems, particularly infotainment, now ADAS. And surprisingly, rather than having the tier ones do that or have the semiconductor companies do it, more and more it's independent companies like Mentor Graphics, where we'll go in and we'll do the embedded software, and then we'll help the various chip suppliers to demonstrate their chips with our software. We'll give them reference design boards and things like that. And then the elimination occurs, and eventually the OEM chooses a tier one, they choose a semiconductor supplier, and then we work together with all of them to get the embedded software working together, and it's a whole different model. We had a lot of trouble in the embedded software business 10 years ago selling directly to the OEMs. Now we're in virtually every competition.
The automakers have a reputation for squeezing every last penny out of the design
Absolutely.
chain.
Yes.
Is that still true? Are they more willing to, because this is something new, that they're willing to invest a little bit more than in the past?
Yeah, purchasing is a core competence of the automotive industry, and they are very effective at it. So the good news is that they are used to paying for expensive subsystems and other things, so we are sort of a drop in the bucket compared to the money that is spent in both developing and fielding a new vehicle. So they, like everyone else, have limited resources, and they follow a Pareto, and they beat down the costs of everything they can, but they can't get too far down the Pareto. And so one benefit is that we're replacing a lot of expensive stuff with alternative solutions that cost less, software for hardware, for example. And but the other side of it is they will beat us down as well. But that actually is nothing new for the EDA industry. We're used to being beaten. And if you don't have something that is really valuable, then it's a very tough fight.
You mentioned software, and there's been a lot of talk now that the people coming into the industry don't necessarily understand hardware. They understand software more. As a matter of fact, the number of software engineers being hired by companies, even chip companies, is probably in the range of 2 to 3 to 1 for the hardware versus the software. What changes from the...
Talking which ratio?
No, the software engineers outnumber the hardware guys by quite a bit. As that begins to grow, as these guys become more a part of the design process, and they're already pretty well embedded, what has to happen in terms of the hardware? Does the software now define the hardware, or does the hardware define the software?
Well, the more and more of the differentiation of a vehicle comes from its software. First of all, I'd say it used to be that the mechanical design was what defined a vehicle, and today it's more and more the electronics, and then more and more over time it becomes the software with the electronics. And this applies to almost all of IoT as well. It's that when more of the value is coming from the software, the semiconductor suppliers either differentiate through their own embedded software or applications or cooperation with people who are creating it, or they have a lot of trouble generating the value. The automotive semiconductor purchases grow about 6% a year, which actually in today's semiconductor industry is not that bad. That's better than zero for the overall industry, but it's not that good either. And so for the amount of effort that's going into automotive electronics, I think the semiconductor companies are hoping to get a bigger piece of the pie, and that means more and more software development that goes around the chips they provide.
How do you see the IoT unfolding? I'm not even quite sure how to define it, because everybody I talk to has a different definition. What's your perception of it, and how do you build mentor into this world?
Yes, so I don't think anyone really knows what the killer apps are going to be, but they suspect that they're going to come from the application expertise side rather than the semiconductor expertise side. So the great thing about IoT is it involves millions or even billions of parts. The bad news is that they have to be very low priced and very low power, and the semiconductor content as part of the total solution is probably a smaller part. In our own case, as this became more and more evident, we discovered almost by accident that the people who are creating these innovative applications aren't used to doing big, complex, integrated circuits. The chip is just a part of the solution they provide, and so all of a sudden they wanted to do chip design, but they didn't have CAD organizations, they didn't have infrastructure, and so they showed up. The company across the way, Tanner, had all sorts of people doing all sorts of weird things, doing MEMS devices, doing sort of entry-level IC design, and it was coming from all sorts of weird places. So it's now my new compass for what's the world of IoT evolving to. I just go and ask Greg Lebsek, okay, what's the weirdest order you got this last week? Because people are doing all sorts of stuff, and like every transition, we can't predict who will be the winners and the losers, so you have to be out there with a big funnel capturing as much as you can of the opportunities, because somebody will end up being a driver of a lot of the volume.
I think the initial perception was that you would be talking to or interfacing much more with your refrigerator or washing machine. The newer perception is that lots of devices will be connected, but not necessarily to each other or other markets, even though that is some long-range plan, right? So how do you fit in all these different stages into the design through verification process?
Well, like every industry, it's not a universal enterprise solution that comes out of the sky and everyone adopts. It's piece by piece. You have expertise in a particular area. You now have the benefit that the data is in the cloud, so you can get access to all sorts of other sources of data that way, and then you build your application. And the question is, so what's the expertise that the EDA industry brings? We bring design expertise, so for chips, modules, complex packaging, as well as for the other end, the big data processing, networking, servers, all that. There are plenty of growth opportunities, and there are all the gateways in between that seem to be proliferating at a rapid rate. But I think the other part is EDA companies more and more are providing embedded software and other types of application expertise and building their own niches. Certainly we are. It's getting embedded software is getting to be a significant percentage of our revenue because that's where the opportunity is.
One of the big gating factors on the IoT has been security. And we've seen all sorts of really interesting stories like hacking into cars as they're moving and things like that. Where's your play from a design standpoint? And you are doing embedded software as well.
Yeah, so we have a great deal of activity in security. Any of you who are interested, Serge Leaf is wandering around here. He can talk to you some. But there are lots of levels where it becomes important. One is simply on the embedded software side. How do you get hack-proof systems? There are a variety of techniques. There are standard approaches, open source approaches. There are proprietary ones. And so there's a lot of software development. There are also issues associated with the integrity of the supply chain of semiconductors, where we have to do something to get counterfeit chips or reused chips off the market. And that means you have to have identification capability built into the chip. And those capabilities are another design opportunity for the EDA industry. And then last is the embedded Trojans. How do you even detect one if you have it, and how do you prevent it getting in your supply chain? And when you look at all the IP that's designed into chips, and the amount of it that has pulled things from open source community and websites and other things, this is a very leaky supply chain for the designer of a chip. So you're going to have techniques built into the chips to not only detect Trojans and other unwanted sources, but also to have defenses against them.
Just sort of like make sure you pack your own parachute, right?
I guess, yeah, maybe.
But one of the issues is, can we use current tools that we have now? Verification, for example, formal tools are pretty obvious, but you can only search for what you know is out there, not necessarily what you think might be out there in the system, or go hunting around for potential problems. Can we start expanding the current tools and be able to use those for the design and say, this is now a secure system, we can build this in?
Well, so we definitely have to build on the current tools, because people who are designing integrated circuits are not going to adopt a whole new tool set just to design secure integrated circuits. So it's an add-on to the existing flow, but it's not a trivial add-on. And I gave a keynote a number of times this year on design for security. And one of the things I hypothesized is that if you look today, there are techniques that are a very high level of security. The military has used them for quite some time. PUFs, for example, physically unclonable functions and things like that. Things you can build into a design to make it very secure, but the problem is it costs money. It adds to the cost of a chip. And so people who manufacture chips spend as much money as they need to satisfy their customer needs. If their customers don't tell them they need security, they don't spend the money to give them security. So I expect sometime we'll see some kind of incident that involves financial loss or loss of life or something like that related to an embedded Trojan in a chip or something like that. And as a result, there will be a counter reaction, and the users, purchasers of integrated circuits will come back to their supplier and say, just sign this statement right here that says you will guarantee there are no embedded Trojans in the chips you're selling me. And they'll send that to your legal department, and the legal department will say, don't sign that. And all of a sudden, there will be a rush to, okay, what can we guarantee? And then you'll find out best practices allow you to do a great deal more than what the average design is doing today. And then security will be another growth area for EDA, and it's only a matter of time.
I think we've heard about some of that in the past, and there's been some repercussions, but it's been very narrow. Is it starting to expand? Are you starting to see those kinds of people coming back to you saying, we do need it now, we are willing to work with it?
We have searched the internet for any reportable case of an embedded Trojan in a chip. We've only found one reported, and it was fairly minor, and I won't tell on the people who reported it because I think it would be healthy if people reported it. But we go to these black agencies in Washington and we ask the question, so why are we worried about embedded Trojans in chips? You know, we can't even name a case where this has ever happened. And these people then roll their eyes back like this and say, oh, and they won't tell you, but I have to believe that if they haven't seen it, they've been doing it to the other people for a long time, and so they believe this is truly a problem out in time.
Well, part of the problem in security is that the bad guys all talk to each other over the internet, but the good guys never tell what happened because they don't want it out there.
Yeah, well, this is, of course, nobody wants to reveal problems with their own products, but the Black Hat Conference has become a major event. We send people to the Black Hat Conference, and there's another one right after it. I've forgotten, what's the name of the other one? That's the DEF CON, yes. DEF CON actually is the parent of Black Hat, but I'm told, I haven't been to Black Hat, but I'm told that you've got two types of people walking around. You've got the ones with a lot of piercings, tattoos, long hair, and then you've got these people in suits, and it's pretty easy to tell which are which. But they're pretty openly exchanging techniques. Now, DEF CON's a little more restrictive. In fact, one year they didn't even allow the good guys to attend, but there again, they have hackathon contests and other things and challenges both sides. So it's a very lively, active area, lots of opportunity for innovation, lots of fun, and ultimately a design problem as well.
And the one place that you never take the handouts from on the USB.
In fact, that's true. At DEF CON, you are not allowed to pay with a credit card because they know what happens to credit card numbers. So you have to pay in cash if you attend DEF CON.
Which sort of leads to another area. If you tackle security, security has to be done not just at a chip level, although it does have to be done at every level within the chip as well as the entire software stack. But it has to be done as a system issue too. We've been talking about system issues and dealing with system level design as a real system for quite some time. Are we starting to move into that direction, particularly as we start moving into the IoT?
Yeah, so I think this is a fundamental issue for all of EDA, and that is that there is an evolution that occurs in the adoption of automation. And I've watched it over my career. I began in the semiconductor industry where things were largely manual. I shouldn't admit this. SPICE was not introduced until after I was designing integrated circuits. And we did one of my early jobs as an engineering manager, we did 30 chips a year without any design verification, without simulation. The only thing we did actually was we tested the chips on our own emulators that we built. And we've evolved to the point where 100% of integrated circuit design is automated. It's done on computers. Well, if you visit systems companies, everything from planes, trains, automobiles, big systems, wafer steppers, whatever, these people are in the early stages of adoption of automation. Many things still done semi-manually that over time, as complexity grows, will have to be automated. So the reason the EDA industry grew at 15% plus for 20 years was because the problems kept getting more complex and they required automation, and the things you did last year in a semi-manual fashion, now you had to do in an automated fashion. And the same thing is happening in the automotive industry, the aerospace industry. The complexity has grown to the point where people like to use the old technique, but they just can't anymore. The system is breaking, and it's creating big opportunities, and the systems industry is enormous compared to the integrated circuit industry. The semiconductor industry is $350 billion a year. The electronic equipment business is trillions, so it's a big opportunity.
So what are we looking at in terms of design? Is it really follow the signal anymore, or is it follow the data? Is there a difference going on there?
Well, by its very nature, it's a system verification, so you're following the system function down to as low as you have to go. I think some of the differences, when SPICE came out, we had a lot of designers who said, yeah, you college kids can play with that thing, but I know how to design an integrated circuit. And the W over L's, they'd all sort of, figure them out or calculate them, and they'd do the schematic and lay it out, and we'd run it through the fab 5 or 10 times, and eventually we could match a data sheet. Well, the system industry is not too different from that now. If you go into even an automotive company, it's not uncommon to go into one of their debug rooms where there'll be a long table with headlights at that end and tail lights at the other end, and all these people with scopes and curve tracers and things in between, testing out this subsystem and that subsystem. That's all got to be done virtually. You can't do something as complex as a car and make those systems work together without virtual design, and same thing on aircraft and other things. So it's an inevitability, but it's a question of which tools, and there's a lot of resistance to change, a lot of skepticism. How can you possibly model anything as complex as the electronic subsystems of a car? And the answer is you have to model them, because no human being can handle all of those constraints and design complexities in their heads, and they will have to do it on computers.
Well, it took until almost probably 65 nanometers before, maybe even 40 nanometers before people put away the spreadsheets and said we now need to use some sort of computational tools. What's where do we hit on the other industries where they say this is the tipping point, we have to go to this kind of tool?
Well, once again, like EDA, ease of use is the method you're using today, and nobody changes until they absolutely have to. So the tool, the flow, the methodology may be slow, it may be poor quality, it may be tough, but it's the one you know. And The one you don't know, you're sure has other problems and you haven't learned those problems, so you keep using the one you have until it becomes not just non-competitive, it becomes unusable. And that usually happens in a new project comes along and you just figure out, I have to change something. Some portion of this has to be automated, and that's when acceptance of technology occurs. And we're seeing it step by step in the automotive industry, in the aerospace industry. They're all going through the same path, and they'll get an electronics problem that simply can't be solved the old way, and then they start looking for, well, what's the new way? And that's when the opportunity occurs. But you've got to be ready at that time. You have to have everything debugged, everything working, and you have to have built the relationship and work through all of the legal issues and other contract issues, and be prepared for the time it actually occurs.
So is this a 1-year plan or a 25-year plan?
It's more like a 25-year, yeah. It's been a 25-year plan. I'm hoping it's a little less going forward, but it's not something that happens quickly. It's slow as people may be to change methodologies and tools in the semiconductor industry, they're lightning fast compared to the automotive and aerospace industry.
You've been working a lot in the embedded software world, and including some open source type of software. How is that market changing? What are you seeing that's going on there that didn't exist maybe a couple years ago?
Well, so one is open source. There are over 35 reviewers and committers of the open source community that work within Mentor, and we've managed to make it a business by adding sufficient value to the what the open source community provides so that it can form the basis for a lot of our embedded software products and environment that we support. So that's a big change. Companies like ours wouldn't even consider open source 10 years ago, something like that. Other changes in embedded software, I mentioned one earlier, is the fact that companies like ours are now trusted by automotive OEMs to provide the basic embedded software for infotainment, for driver assistance, for other things like that. And that wasn't true before. They went through tier ones and semiconductor suppliers and others, and that door has been opened. That's a different part. And then I guess the other thing I'd say about embedded software in general is that you no longer have the let's verify the hardware, and then when the hardware is stable, the software people can do the verification. It's almost everybody is doing some level of embedded software verification at the design level, usually on an emulator, where they're verifying either deeply embedded software, drivers, things like that. And I think over time, that inevitably is going to creep up, and the continuum will occur where you have a point where you tape out, but the verification continues continuously going to higher and higher levels and more volume of application software.
One of the ways that semiconductor industry has been able to progress is through standards, and very good application of pretty narrow standards. Occasionally we mess it up. I can cite one in particular, but I'll leave it off. But as we move forward into more of a system world design, system level design, the standards are going to be much tougher to implement as a road signs that say, here's the way to go forward, because you have so many interactions that are possible, particularly in the IoT. What's your vision about how this unfolds as we go forward?
Well, standards are what makes leverage possible. It allows different companies to compete for the same application. It allows different companies to provide their products into a more diverse solution. So Mentor sort of has a history that is a little different from a typical EDA company. We have always emphasized best in class. We've allowed internal competition for tools, and we depend upon standard interfaces because we have to work equally well in any flow if you're going to sell both point tools as well as subflows, as well as, well, with full flow, you don't need that so much. And so we've had to be involved in the standards committees. We've had to donate a lot of things to standards committees. And while it becomes more complex, I think it's the complexity is really the diversity of interests that have to come together more than the actual technical complexity. And that's a challenge. But the industries of the world will solve it because there is such a big payoff. The thing I worry more about is that if you get too much concentration in one piece of the solution, then people start to decide that they're giving more than they're getting from the standard interface, and those interfaces become less open, and then that that slows innovation. That causes the whole industry to slow down.
I have one last question for you, and I saved for the end. Patents. So patents have been actually ignoring patents has been one of the ways that the semiconductor industry and technology progress so well, all the way back into the day. I'm gone.
Uh-oh. Battery replacement. Okay.
I've got the new low power mic. Patents have enabled, non-enforcement of patents has enabled a lot of the industry to move forward. We now have a patent system which is by best, putting it nicely, a mess. What's your opinion about how we move forward with patents? What has to happen, and how does that have to change?
Well, as you noted, the semiconductor industry had a level playing field for patents because Bell Labs licensed 50 companies right from the start, and so the industry as a whole decided not to waste time with patents. They all cross-licensed, and until 1982, basically everyone could stand on everyone else's shoulders, and you had the most rapid period of open innovation in the history of the world. And the patent system was largely ignored. Then in '82, the Copyright Protection Act was enacted, and that then put a big damper on this. And also, I would note my former employer, who had emphasized the only reason we file patents is for defense, suddenly decided to go on the offense. So the world started to change, and then as we came into the 90s and the subsequent decade, we had software patents, many of which were of questionable distinction, and the system went out of control. And so now I think companies like ours file patents in a prolific manner for defensive reasons. We don't file patents in order to go sue someone. That's not our objective. And it's not clear to me that anyone wins in any of these lawsuits anyway, except for the lawyers. So the question is, what can be done? Congress has taken action in changing things. The courts have been more critical of patents. We now have a re-review process that's been used effectively to invalidate patents that weren't differentiated. So I think there's some improvements being made, but it's very hard for companies to get the legal benefit of patents if the price tag of defending a patent is so exorbitant that small companies can't afford it, and even big companies have trouble affording it. So I think the system does have to evolve and become move a little in the other direction toward protecting people as opposed to protecting lawyers.
Thank you very much.
Okay, thank you.